Welcome back. This is the final lesson for Unit 1, Data Representation. In this lesson, we're going to be looking at data storage and compression. By the end of this lesson, you should be able to understand how data storage is measured, and you should be able to calculate the file size of an image file and a sound file using the information given to you. You should also be able to understand the purpose of and need for data compression and understand how files are compressed using both lossy and lossless compression methods. Let's begin by looking at data storage. Now, in previous syllabuses, you needed to understand the differences between kilo, mega, giga, and terabytes. However, for the purpose of our exam, we're only interested in kibibytes, mebibytes, gigabytes, and terabytes. You need to make sure that you understand the distinction between both of them because previous exam questions might refer to kilobytes rather than kibibytes, and that could cause some confusion. So we're just going to go through a basic skit on how a layman and an expert, a computer scientist, deals with the differences between both. So on our left, we have a layman, a person on the street who doesn't know the difference between kilobytes and kibibytes, and on the right-hand side, you have an IGCSE student. So the layman goes, computers work with electricity. The student goes, that's true, but computers use binary, which is base 2, which means 0 or 1, electricity off or on. So there's a lot more depth to their answer since we know about binary now. The layman goes, well, a kilo is 1,000. So kilobytes are basically 1,000 bytes. The student goes, in base 2 we use geometric sequencing. So 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So 1024 is known as kilobinary or kibi. So it's not exactly 1,000. Well, the layman goes, mega is a million, right? And the student goes, well, actually, it's 1,048,576, which is known as mega binary. So the layman goes, why the two different approaches? The IGCSE student says, well, because of systems international units. To make it easy for non-experts and laymen to remember, these are called decimal prefixes or base 10 prefixes like kilo, mega, giga, and so on. So the layman goes, now I'm a bit confused. GB is still gigabyte, right? And the IGCSE student goes, well, that's right. However, GIB is gigabyte, and 1 gigabyte hard drive, 1 GB hard drive will be smaller than 1 gigabyte hard drive because GB uses base 10 and GIB uses base 2. So the layman goes, okay, so 1 TIB, 1 terabyte, is more than 1 terabyte. And the IGCSE student goes, well, you got it. 1 terabyte is the equivalent to more than a trillion bytes. 1,099,511,627,776 to be exact. So that approximately 99 billion extra bytes are only given to you in 1 terabyte or terabinary byte equivalent rather than a terabyte. Okay, apart from that little skit, why do we use decimal prefixes? Well, because we're used to them. This is the standard metric system for prefixes: kilo, mega, giga. Decimal system increases in orders of thousands. We know it, we use it every day. So you got a kilo, like a kilogram or a kilometer. You got million, you got billion, and all of those kind of things. So what happened was that it was very easy to transfer this to the computer world. And the reason we did that is because at the end, consumer is king. To make it easier for non-experts, we wanted to adopt a simple system. And this was great when storage capacities were tiny, but as storage increased in size, decimal prefixes were still being used, which basically means megabytes and kilobytes were still very common. So a kilobyte could equal 1,000 bytes or 1024 bytes. The difference is very small. 1024 bytes was close enough to 1,000 for people to decide to just use kilo as the prefix. And when we went to a megabyte, 1 million bytes or 1,048,576 bytes were sufficiently close enough not to make too much of a difference. However, as storage capacities increase, things got a lot more messier. When we look at gigabytes and terabytes, you're looking at the difference in terabyte stages of 99 billion or so extra bytes. That's a huge amount of capacity. Therefore, we had a problem because people couldn't tell when they used megabytes whether they were getting 10 million bytes or they were getting 10,485,760 bytes. Nobody knew what the storage capacity was when we used megabytes. And yes, storage was that expensive in the old days. Imagine a 10 megabyte hard drive costing $3,495. In the early days of computing, prices were really expensive. That's probably the same equivalent now. If you wanted to buy exabyte hard drives, they probably cost you the same amount of money. So what was the solution to all of this? Well, the solution was binary prefixes. The industry then decided to get their heads together and come up with a new prefix system for binary units in order to avoid this confusion. And in 2005, the IEEE approved the binary prefix as the new standard. So kilobinary, megabinary, gigabinary, terabinary, and so on became the norm. So kibi, mebi, gibi, and tebi, or ki, mi, giti, they were the prefixes we use in front of bytes. So they became kib, mib, gib, tib. And these go up in base 2. So 2 to the power of 10 is equal to 1024 bytes, which is 1 kib, not 1 kb. So the order that you need to remember for the exam is the one on screen. Bits are 1 or 0. That's the smallest unit of data. Nibble is 4 bits. Byte is 8 bits. Kibibyte or KIB is 1024 bytes. Mebibyte, MIB, is 1024 KIB, so it's 1024 the previous prefix. So to work out how many bytes there are in the mebibyte, you need to do 1024 times 1024 bytes, because KIB is 1024 bytes. That gives you 1,048,576 bytes. Gibibytes, GIB, is 1024 MIB. Tebibytes is TIB, 1024 GIB. PIB is 1024 TIB, and so on. Now, this is the only order you should remember. Older exam questions on the internet use denary prefixes like KB and MB, so be aware of that. You must not use 1000, 1,000,000 in your exam. You'll get the answer wrong. You have to use binary prefixes 1024 based. So the example that you see on screen is 4 MB is 4 million bytes. That's 4 times 1,000 times 1,000. We can't use that one. We have to use 4 MIB, which is 4 times 1024 times 1024. So modern exam questions will use this method. So how do we use this in calculations? You'll be given exam questions where you need to work out the file size of something, either an image or a sound file. So we're going to look at both of these separately. So calculating bitmap image file sizes is first. If we have an image of, let's say, 1920 times 1080 resolution and a bit depth of 24, how do we work out the file size? Well, we work it out by simply multiplying 1920 by 1080 by 24, which gives us 49,766,400 bits. We then divide this by 8 to get bytes, which in this case now gives us 6,220,800 bytes. And we further divide this by 1024 to get KIB, and then another 1024 to get MIB. So we end up with 5.933 MIB. So the formula is resolution times bit depth equals the file size. And the resolution is the vertical and the horizontal pixels multiplied together. Now be very careful in the exam. So you got to read the exam question carefully. Sometimes they mention the number of colors rather than the bit depth. For example, they'll say 8 colors. Now 8 colors can fit in 3 bits because 2 to the power of 3 gives you 8 rather than using 8 bits straight away. And if we were going to use 24 colors, they could fit into 5 bits because 2 to the power of 5 gives you 32 combinations and 24 can fit into 32. It's also important to know that each bitmap file contains a file header that contains items such as file type, file size, image resolution, bit depth, any type of compression used, and so on. So there will be some extra data in addition to whatever the file size calculation is. However, that type of question is normally a descriptive question and isn't a part of the actual file size question. So how do we calculate the sound file sizes? John records a 10-second sound with a sample rate of 10 kilohertz and a sampling resolution of 16-bit. What is the file size in bytes? Well, in this case, we've got 10 seconds. So we do 10 times 10,000 because 10 kilo is 10,000 times 16. So that gives you around 16 million bits. You divide this by 8, that gives you 2 million bytes. So the formula is sample rate times sampling resolution times track length is equal to the file size in bits. Now here, be careful of the use of minutes. If you're given minutes or hours, you need to convert them into seconds first, because kilohertz is in seconds, it's frequency. And sometimes they might use 2 channels for stereo, for example. You will have left and right channels, so you have to multiply it further by 2. So those are the extra little bits you need to think about with sound. Okay, that's enough about file sizes and calculations. Let's look at the need for compression. And compression exists to reduce the size of the file. When we are dealing with files which go into terabinary, these file sizes are huge. So we need to make sure that we reduce this file size to save storage space, make it faster to transmit online, things like that. So the original file is resaved after passing it through an algorithm, a compression algorithm. As a result, less storage space is now required to store the file. And the impact of this is that less bandwidth is required if you want to transfer the file online, and the shorter transmission time is therefore needed. Now, there are two types of compression algorithms that you need to be aware of: lossless and lossy. No data is removed in a lossless compression algorithm. So all the data bits from the original file are fully reconstructed when the file is uncompressed. This type of compression is important for files where any data loss would be a disaster, for example, a spreadsheet or a text file. Now, an example of this is in text files, if there are repeated words or sections of words which can be replaced with something shorter. For example, the word the can be replaced by one, and every time one occurs, you just fill the word the in that particular place. Now you're saving two ASCII characters every time the occurs in your paragraph. A common lossless algorithm is run length encoding algorithm, RLE. And RLE is only effective when there is a long run of repeated units and bits. So it works exactly like the example we mentioned earlier. So what's happening on screen is you've got a series of A's and a series of B's and some C's. The RLE algorithm groups together repeating patterns and indexes them. So what happens is we pass the data through RLE and it will now say, well, there are 8 A's, 6 B's, and 2 C's. So if the original data was 16 bytes, because each extended ASCII character takes a byte, therefore we now have 6 bytes to represent the same set of data, because the computer knows, well, okay, the first one is the number of repeats and the second one is data. So 8A. When I uncompress, I have to write down 8 A's, then 6 B's, and then 2 C's, and it will restore the original pretty easily. What happens when the string isn't straightforward? So if you look at the data on screen, it's a bit trickier. In this case, the original 32 bytes are encoded into 18 bytes. However, we can compress this further by introducing a flag where if the data is going to be repeated, we identify it with a flag, 255 in our case. And if it's not, then we just leave it as is. So the original becomes 255 because we're going to repeat 5 times 97. Then 255, which means we're going to repeat 4 times 98. 98 is ASCII B. 99, 100, 99, 100, 99, 100, CD, CD, all of that becomes normal. And towards the end, we repeat E 5 times. And we say that by 255, this is a repeat flag, repeat 5 times, 101, which is ASCII for an E. This now gives us 15 bytes, which is an overall reduction of 53% from 32. And in this way, people keep on refining compression algorithms to save more and more space over time. Now, RLE is not just used with text. RLE can also be used with images and pixels in particular. For black and white images, RLE works the same way. 1 for white and 0 for black, or vice versa. The grid would be recorded. For example, every single pixel would be recorded. So the original character that you see on screen requires 64 bytes, but in the RLE format, it only needs 30 bytes. And you can pause the video to see that example and study it. But in the exam, chances are they'll be giving you this type of structure and asks you to work out the maths behind it. For color images, we normally use an index to represent all the colors or repeating patterns, and then we use those values to compress the data. So you might simply say that this set of pixels is represented by this code, and then we just use that code in the compression. In addition to the compression data, the resolution of the image is also stored with the data, so the computer knows the size to recreate when it decompresses. So that's some additional bit of information which is known as metadata that's also stored with RLE. Now that's all about RLE. You should be able to describe what RLE is. It's a lossless compression algorithm. It identifies repeated patterns and it encodes data into normally two values. The first one is normally the repeat and the second one is the actual data. It can also use indexes and flags to further compress the data. When you decompress it, the original is fully restored. Okay, that was lossless compression algorithms. There's another type of algorithm which is called lossy compression algorithms, and this algorithm eliminates unnecessary bits of data to compress a file. The original data cannot be fully restored upon decompression. This one saves more space, however, you don't get your full data back. Now, in MP3 files, this is in the form of perceptual music shaping. We'll look at that in a moment, which means sounds that the human ear can't hear are removed to reduce size. In JPEG files or photographs or images, this is dependent on the limitation of human vision. For example, colors which we can't see, colors which are closer together, and this is done by reducing the color depth, or perhaps the image resolution is tweaked. In MP4 video files, a variety of methods are used, such as removing some of the color information in each frame, or removing parts of the video which don't really move or change. For example, if you're recording a video and your background doesn't change, so it only records the pixels that change and it keeps the background the same, so it doesn't need to repeat it for every single frame, and that's what it uses for compression. Okay, we mentioned perceptual music shaping, and this is quite important because you could be asked how perceptual music shaping helps in reducing sound file sizes. Well, perceptual music shaping removes sounds that we can't hear. For example, frequencies outside human hearing range. And if two sounds are played at the same time, the louder one can be heard and the softer one can be removed. So perceptual music shaping removes these types of sounds. Now, the quality isn't affected too much because we don't really hear those things in the first place. However, since parts of the original file are removed, this is known as a lossy format. Now, depending on the bit rates, the quality of sound can also change. So for example, if we were recording things in MP3, we could record it in 80 kilobits per second, which is quite poor, or you can use 200 kilobits per second, which is closer to CD quality, or up to 320 kilobits per second, which is high quality sound. All of this is still compression, so if you're using 80 kilobits, you're probably removing more of the original sound compared to in 320 kilobits, where less of the original sound is removed. Now, there are some additional methods of compressing without algorithms, and these involve for images cropping the image, decreasing the color depth or bit depth, reducing the resolution. You're not using a compression algorithm, but you're just resaving the file. However, these are still destructive. That means you can't get the original back. For movies and sound, you can reduce the sampling rate, you can reduce the sampling resolution, and for movies, you can reduce the frame rate as well. All of this is still destructive, so this is lossy. Okay, that's enough for this particular lesson. You should be able to answer the following questions. How many times would you need to divide bytes by 1024 to get a gigabinary byte? You should also be able to list the order of data storage in increasing size order. You should also be able to compare benefits and disadvantages of lossy and lossless compression. You should be able to explain what is meant by perceptual music shaping, and you should be able to explain the use of run length encoding, RLE. And with that, we finish off Unit 1, Data Representation. If you do have any questions, please do get back to me. Otherwise, I'll see you in the next one.